Hey everybody. So today we're doing our lesson. It's 9.4. This is Friday's lesson. Um, and what we're doing now is we're taking kind of the next natural step in studying these exponential functions. Okay. We're going to dive a little bit deeper today, looking at specifically two kind of special flavors of exponential functions: growth and decay. Last time we looked at how the graphs looked, we looked at how to solve them, and we're diving a little bit deeper into them. Okay, so you've probably heard that riddle or that puzzle, where if I had a job for you to do, and I offered you either $1,000,000, or I offered you starting at 1 penny, doubling it every day for a month. So you're going to work for me for 30 days. You could take $1,000, or you could take starting at 1 penny, and then I would double it the next day to get 2 pennies, and then the next day I would give you 4 pennies, and you just keep doubling it. Well, which would you take? A lot of people say, "Oh, I'll take the $1,000,000." But I can tell you, taking the penny, doubling each day for 30 days, just your last day's pay, just that much pay would be over $1,000,000,000. So a lot more than 1,000,000. So growing exponentially, things grow really fastly at some point. So it's kind of an interesting concept. But let me stop talking about riddles and actually jump into the math for today. So I do want to say that we did mention this last lesson. So let's get growth versus decay. So I would like to first write what the equation would look like. Now the textbook is going to tell you that it'll look like this: b to the x, and it all depends on what this b value is. That's whether you have growth or decay. Okay, whatever this b value is. So if this base is bigger than 1, greater than 1, so say it's something like 3 to the x, or 1.2 to the x, or 5/4 to the x, which is bigger than 1, then you have growth. If it's in between 0 and 1, then you're going to have decay. So something like 0.5 to the x, or 0.011 to the x, or 1/2 to the x. Those are all going to be decays. Okay, and we actually know what the graphs are going to look like. I'll do some really fast, sketchy sketches of these, growth and decay. We graphed them last time. I just want to point out a few things. Okay, growth is going to start really low back here and shoot up pretty fast. Okay, and decay is going to start really high and shrink down pretty fast and then take a long time. Now remember, these graphs have asymptotes, so that means they never cross some line that shoots across horizontally here. They get really, really close to it. Okay. Now I do want to point out that both of these graphs, no matter if they're growth or decay, will have 2 points on them. Okay. These graphs, both of them will have the point right here, which is the point 0, 1. Okay. And that just comes from the fact that if anything to the 0th power equals 1, and then they both will have this point here, 1, and then whatever the base is the y value. Same thing here, 1, and then whatever the base is. Just some points on the graph where you could sketch these really quickly, just knowing whether it's growth or decay, knowing it's going to cross at 0, 1, and then 1b, whatever b is. Okay, so that's how things look. So let's talk about modeling growth and decay now. Okay, so I give you some fancy word problem, and I say, it's growing exponentially. Can we model it? Modeling. So yes, y'all are going to become models today. Modeling growth. So here's how this is going to look. Okay, we're going to have some number. We're going to call it c for now. And it's going to be multiplied by 1 plus r to the x. Okay. Now let me label these pieces. C is your starting amount. So you started with $5. You put it in a savings account. how much is it going to grow? And so there's your $5. This whole piece in parentheses right here, that whole piece, which would be like the B, that whole piece is the growth factor. Growth factor. Oops, I forgot the W. Growth factor. Not that you need to memorize this. It's just if I mention the terminology, I want you to know what I'm talking about. And R is the growth rate. Growth rate. That's usually going to be some sort of percentage that we'll have to model as a decimal. Okay. And so I can easily say, okay, so you start with 5 bunnies, and they're growing exponentially at a growth rate of 2%. So 1 plus 2% to the x. How many bunnies will you have in so many days? You know, so you could model growth that way. We can also model decay with a very, very similar formula. The only difference in modeling decay versus modeling growth, you still got the starting amount, you still have 1, you still have R, you still have X, but instead of adding the growth rate, we're subtracting it because it's the decay rate, and this is the decay factor. Okay? So this is the decay factor in here. Decay factor. And R is the decay rate. Decay rate. And C is still your starting number. Now this looks very much like those formulas that we did for money, interest. Very similar to that. Okay, so if you're growing, we're adding the rate. If we're decaying, we're subtracting the rate. So let me show you what this is going to look like. Okay, I'm going to do 3 examples with you. I do want to mention something. I forgot to label the X. In these decay and growth problems, this is the number of time intervals. So when we did the money that you put in a savings account, the interest problems, the time intervals were years. So if you left it in there 5 years, I could just put a 5 up there, right? Here, the number of time intervals is going to depend on what we tell you in the problem. Like, it is increasing by 3% for each day, then we want to put X in terms of days. Okay, so we put that X in terms of the units that our rate is given in. So we'll get some sort of rate of how much it's growing per day or per week or per second or per hour or per year, and that's what this unit needs to be. Okay, so the units here need to match up. You'll see when I work a few problems. Okay, so let's jump right in. Of course, I've written my own problems. You'll like the worksheet. Please look at the worksheet problems. They're kind of funny. So here we go. To match what we're doing, the number of coronavirus cases in South Carolina is growing exponentially. Each day, the number of cases increases by 4%. So there's a lot of information there. We'll come back to it. Let's finish reading. There are currently 2,552 cases in South Carolina. How many will there be in 10 days? And this actually is the true number as of yesterday, Thursday. So each day, so what unit am I growing per day? Increases by 4%. Okay, increases by 4%. So that's how I know it's growth. Besides the first sentence telling you it's growth, is we're increasing. So that means it's going to be plus R. And what is our R? Our R is 4%. How would I make that a decimal? Divide by 100, or you could just move the decimal twice. That'd be 0.04. And then this is the starting number, right? How many cases are there right now? 2552, that's our C. So can I model the exponential growth of this? Remember the formula looks like this. Okay, so let's see what bit of information we have here. So do I have the starting number C? Yes. 2,552 cases. 1 plus, do I have the rate? Yeah, it's just 0.04. And then finally, I need to know the number of time units. Well, I'm looking at 10 days. what units are we increasing by per day, each day, per day. So then 10 days, that's awesome. That's telling us how many of those time units we have. So to the 10th. Okay. Now when we do this, we're just going to use a calculator. I could do a little bit of math without a calculator, because I'm able to add 1 plus some decimal. That's just going to be 1.04. Whoops, I missed the 0. I can't even do that. There we go. And then we'll just put this in a calculator to get the final answer here. And I've done it for us. It comes out to, so in 10 days, there'll be 3,777.58 cases of coronavirus. Now, there's a little something wrong with that. Can you have 0.58 of a person? No, so we need to round this or approximate this to 3,778 cases of coronavirus. There we go. In South Carolina. Awesome. So let's do a decay example now. Okay. So, we found a great cure for the coronavirus. Yay! The number of people infected is falling by 15%. All right, let's get this. 15% per day. In the U.S., there are currently 434,000 cases. How many cases will there be in 2 weeks? So this is a decay problem. How do I know it's a decay problem? Because the number of cases are falling. That was supposed to be a circle that did not make it all the way around. So I can model this as C1 minus the R to the X. So do I have these numbers? How many cases am I starting at right now? 434,114 as of yesterday. 1 minus, do I have the decay rate? 15%. As a decimal, that'll be 0.15 to the X. Now, do I want to put, don't copy this yet, do I want to put 2 because I have 2 weeks here? Well, wait, this is weeks, this says days. I want this to be in days. So, 2 weeks. How many days does that equal? Well, there's 7 days in a week, so that'll be 14 days. Okay, so 14 of these time periods. So in 14 days, let's see how many people will have, how many people will be infected. So it's falling, so hopefully this should go down. So from 434,000 to 44,613.75. Once again, we're talking people, so I need to round or approximate. So 44,614 cases. Awesome. So that's pretty substantial drop. That's the size of several small towns. All right. Well, that's great. So we've modeled a decay. We've modeled exponential growth. So let's look at one other type of problem. Okay, let's look at what's called a half-life problem. And now half-life problems are exponential decay problems for which they model. They tell you, okay, so it's decaying, and we know the rate at which it's decaying to where how many years it takes to half. Okay, so we made the cure for the coronavirus, but now whatever that material was, it's poisoned the pond at Francis Marion, and we can't go swimming in it. Not that any of us swim in it to begin with, but we need to wait on the poison to get a low enough amount. So the poison has a half-life of 15 years. So every 15 years, the amount of poison halves. There are currently 400 liters of poison in the pond. So that's how much currently we're sitting at. And we want to know in 72 years how much will be left in the pond. So it looks like the same type of problem without some information. Did they give us our rate? They didn't really tell us, but they did tell us this is the half-life. What that means is the R here is a half. What's a half as far as percentages go? That's 50%. We need it as a decimal. What would that be? 0.5. Okay, awesome. So we actually do have the rate. So we're saying, okay, well, we can model this as a decay because we're lucky enough to have the same information. It's just hidden because it's a half-life problem. So what's the current amount? 400 liters. 1 minus a half. Now we have to think about the units. Here's what's weird is the half-life is 15 years. We're looking at 72 years. How can I find the number of 15-year chunks that are in there? That's just a division problem. So that's what we'll do with these half-life problems, is take the half-life and divide it into the total amount of time. So that's our unit, is every 15 years. So 72 divided by 15 is 4.8. So our number of time periods here is 4.8. So now once again it's just a calculator. Plug this into the calculator and let's see what we get. And when we do that, we get about, I'm going to go ahead and round to begin with, 14.4 pounds. So it's a very, very long time later, 70 something years. I probably won't be alive in 70 something years. But it'll be down to 14, not pounds, liters. 14 liters in our pond, in Francis Marion's pond. All right. Now, that's all we're covering today are growth and decay problems and half-life problems. So make sure you do the worksheet that's attached to the email. Answer keys posted. You just get to practice one of each. I think you'll enjoy my problems I've written. Y'all have a wonderful day.